Rebecca will speak about characteristic zero closure operation.
Great, thanks for coming back. So this is very much a and now for something completely different moment. Because I've been working on this for a long time, but it's not at all related to the morning. So on the bright side, if you've forgotten everything, it's totally fine. So this is joint work with Neil Epstein, Peter McDonald, and Carl Schweid. And this comes out of tight closure originally. So I'll go through this in more detail, but let me give you a brief summary of the big idea here, which is that tight closure is like really good for thinking about singularities in characteristic P. In characteristic zero, people use things like the multiplier ideal, and there have been a whole lot of efforts to get something that's tight closure-like in characteristic zero, and I think we have the best one yet. So that's the summary of what the talk's going to be. So let me talk about closure operations. So a closure operation, and I'll usually, if it's not a specific one, I'll probably write CL. And this is a map sending pairs of R modules and we want L to be contained in M to an R module. To be clear, R here can be any ring so far. I have no restrictions on it. It doesn't really have to be commutative even. And we're going to send to an R module that we denote L sub the ambient module superscript, the closure name. And all we need to be a closure operation is that first, the submodule should actually contain L. The closure should contain the thing we're closing. Second, if we apply the closure twice, that should be the same as applying it once. The closure is actually closed.
Sorry, I can't read the first line.
A closure operation, CL, is a map sending pairs of R modules with L contained in M. So the input is L contained in M and the output is the closure.
L contained in
This is L contained in M.
Oh,
Yeah. And finally, if we have two submodules of M and L is contained in N, then we want that to still be true when we take the closure. So L's closure in M should be contained in N's closure in M. It preserves containment. And this is like extremely weak. You can define a lot of things that do this. Send every module to itself, fine. Send every module to the ambient module, fine. Yeah, this is all fine. But one thing that I'm generally going to assume for my closures is that the functorial property and all that means is it's compatible with our module maps. So if we have like F from M to N, and L is some submodule of M, we want, if we apply F to the closure of L and M, to be contained in the closure of F of L in N. So let me do some examples.
there, the closure of M should be M.
Well, it's going to have to be a submodule of M and it's going to have to contain M, so yes.
Oh, yeah. Also, like, what's the closure?
Right. So closure will act on certain pairs L contained in M. M is not, it doesn't always have to be the same M. So you could, for example, have it defined on any pair of our modules where L is contained in M, or any pair where they're both finitely generated, or any pair of graded, or whatever.
So it doesn't have to be defined for every pair. just
No.
some.
Some pairs. It's really common to do all modules or all finitely generated modules. In some of my papers with Neil Epstein and Janet Vasiliev, we get to like more specifics on which modules you need to have the closure defined for. That's finickier than you need most of the time. So the first example is the trivial closure. And right, it's just send everything to itself. And it's not like this is an especially useful closure on its own, but it's useful to say that another closure is trivial. Second, are an example I've been working with for a pretty long time. These are module closures. So B is an R module. B short for possibly big, may not be finitely generated. And we'll have L contained in M. So then the CLB is going to denote the module closure coming from B. And this is going to be defined to be the set of elements of M such that B tensor X is in the image of B tensor L to B tensor M for all B and B. The idea here is maybe X isn't quite in L, but if we tensor with the right thing, it'll end up in the image of L. And this isn't always so bad. If B is an ideal, sorry, if L is an ideal, if L is an ideal, then if we look at the closure of I and R, this is actually just going to be a colon ideal. Everything that multiplies B into IB, because we can view that tensor as just multiplication.
Which are operators that form a category?
Probably, and I haven't tried to work out details, but probably. I think the place where people have been most likely to think about this is if you look at people who study star operations or semi-prime, sometimes they try to classify all of the star or semi-prime operations for a ring. So they might have thought about closure operations making a category. So third is really the motivating example for this talk. I'm going to define this in an extremely limited case. So for tight closure, R is a domain of characteristic P. And I will be an ideal, and I'm going to give a list of generators for I. So then I star equals the set of X in R such that there exists some C not equal to 0, because I assume domain for people who know tight closure, such that for all E sufficiently large, C X to the P to the E is in the ideal generated by the P to the E powers of the Fs. Things to note about this definition. I really limited where I defined it for. You can define it. You don't need a domain. You don't need to be just for ideals. This is defined on all modules. It's just messier the more you do that. So also, this C has to work for every E, but this C may not work for other X's. So one of the tricky things about tight closure is if you're trying to check if something's in the tight closure, you have to find the C. And it's sort of hard to prove that a C doesn't exist in a lot of cases. It's extremely hard to compute. But it's been used to describe most of the common classes of singularities in characteristic P rings. And it turns out that via reduction to characteristic P, these do correspond to equal characteristic 0 singularity classes. So if we have, for example, every submodule of every module is tightly closed. This is a way of saying, of describing something called strongly F regular. And that is going to correspond in characteristic 0 to log terminal singularities, or KLT, depending on conditions, which I can't describe. So then if you look at every parameter ideal, So ideal is generated by a system, part of a system of parameters. So if every parameter ideal is tightly closed, that corresponds to something called F rational, which actually does correspond to rational singularities in characteristic 0. So if you're like, I would really like to know all the correspondences, these results are from a lot of people, Hoxter, Hunicke, Smith, whole bunch of other people have worked on this. If you want to look this up though, my recommendation is there's a survey paper by Carl Schweid and Kevin Tucker. And that's just, they literally have a chart in the back of the paper that lists all the correspondences of singularity types. It's my favorite place to look this up.
Is this for a local ring or just a general domain? We're speaking about the whole spec.
So this gets complicated in that often in the characteristic 0 case, you want to be like essentially a finite type over a field containing C or something. And then in characteristic P, you often want to be complete. And so I don't want to give all these details because it's a little bit complicated. So this is all framed in terms of tight closure, but really the tool that people actually mostly use, and that's more commonly in correspondence, is the test ideal. So I'm going to define this for an arbitrary closure, but it is the tight closure definition. So for this, we want CL to be a closure operation on all R modules and their submodules. Then the CL test ideal is the set of elements of R that are in this intersection. So we look at everything that, multiplies the closures back into the original submodules. If the closure is trivial, this will be the whole ring. So that's not how, so this is like, if you put tight closure in here, this is correct. This gives you the tight closure test ideal. But the reason it's called the test ideal is because of these C's. So a test element is a C that'll work for any check you want to make of whether something is in a tight closure. And it turns out that will agree with this definition. That's mostly context, not critical for the rest of the talk.
It's C saying various things on the end, right?
Yeah,
Is
so
there
it,
a C that works for everything?
if a test element exists, then yes. And Hoxter and Hunicke have a lot of results on test elements existing most of the time. Certainly complete, I think excellent as well. Yeah. So you could also do this, for example, restricting to these being finitely generated, or restricting to L as a parameter ideal. There's a bunch of restrictions you can take and get variations on the test ideal. And a thing to know about this is the multiplier ideal is going to reduce to this. Let me give you a definition for the multiplier ideal. There are many. I'm presenting this as a theorem because it's not the usual definition of the multiplier ideal, but this is from Peter McDonald's thesis. So let R be a normal, excellent domain containing Q. And we need it to have a dualizing complex. It's like a canonical module if you can't get a canonical module. A little bit. So in this case, the multiplier ideal is going to be given by the following. So fancy J of R will be the sum So we're taking the sum over regular alterations. If you're like, I don't know what this is, great, I'm with you, you can black box this. And we look at the images of Hom from this canonical module into R, tensored over R with the canonical
Unique set equalizing complex or
complex. Yeah.
that's a CX there. I see.
Oh, I probably should have written that out the first time, yeah. So this map, like this map is the evaluation map. So if you just want to look at the algebra part of this structure, this is saying you look at maps from this canonical thing to R, and then basically you take a map from the canonical thing to R and an element of the canonical thing, apply it, you end up in R. So like phi tensor, I don't know, U maps to phi of U.
Sorry, I'm sorry, so inside the Hom,
Mhm.
what is that? That's a.
Global sections of the canonical module for Y. Yeah, and this is where we start to get into the fact that I'm not a geometer and I'm putting these on the board and I can mostly tell you how I use them in a commutative algebra context. I'm probably not going to be able to fill in too much about the geometric things. The point is regular alterations are something people often look at in characteristic zero. So under some circumstances, the multiplier ideal looks like this. And in more generally, if you reduce the multiplier ideal, you get the tight closure test ideal. I think, okay, this is the result. Karen Smith got this and another group got it at the same time and I have forgotten to write down their names. But this is known. So I'll say Smith and others. So a thing we might want to know is what does the test ideal actually look like for other closures? If we're trying to talk about the multiplier ideal, the test ideal, get some closure that maybe has this as its test ideal, we might want to know some results on how to work with test ideals of other closures.
Overall, maps Y to spec of R.
Regular alterations specifically. Yeah.
What's a regular operation? Is that
It's the definition I can give on the fly is it's not as strong as a resolution of singularities, but it's a similar vein kind of thing. In particular, you could look at resolutions of singularities here. I do have definitions written down. If I try to give them on the fly, I will just fail. So, so I need one more quick definition. A closure operation, CL, is residual if whenever we have a containment like this, the closure of N and M, we can compute by basically modding out by L, taking the closure there, and then pulling back up where pi is the quotient map from M to M mod of L. All this means is plays well with modding out by submodules. And I needed that just so I could say. So this is an older result of mine with Felipe Perez. So if R is local and CL is both functorial and residual, then we can write the test ideal for this closure actually as this annihilator in R of the closure of zero in the injective hull of the residue field. Which is something that was done for tight closure already. The idea wasn't new, It just turns out you don't need very much of an assumption on the closure to get it. And stronger if CL is a module closure. Then tau CL of R is actually going to be a trace ideal. And I'm sorry, Heidi's not here for this, but she knows. Where the trace ideal is going to be the set of all X in R. No, let me write this differently. It's going to be the image of Hom from B to R, tensor B to R, where this is evaluation.
So what's E of K? Is that the
Injective hull of the
and
residue
is that-
field.
Is there some P on it or?
No,
Oh,
we're assuming R is local here.
oh, it's E sub R.
Oh, yeah. So if you're looking at this, a thing to pay attention to is look at this structure over here with the trace ideal and look at that definition of the multiplier ideal. And they look very alike, which is actually what started this research, was that Carl sent Peter to visit me and Neil because he said, this looks like something you might be able to get a handle on. Sure enough, that's true. So before I get into our definitions, I want to briefly talk about what our options so far have been for characteristic zero closure operations. This is going to be extremely brief and not do them justice because mostly the point of this talk is not to focus on them. So one is equational tight closure. And that's Hochster and Hunicke. I've worked on this. And essentially how you get this is you reduce to characteristic P. Via a finitely generated Z algebra. I'm not going to go into details for that. The point here is it is a characteristic zero closure. You have to reduce to characteristic P in order to define and use it. Second are non-standard tight closure. And generic tight closure. These are defined by Schoutens. And here, it's still a reduction to characteristic P, but it's by a different method. So you use ultra products. So it's a different method of reduction to characteristic P, but again, this is a reduction to characteristic P kind of closure. It's not like inherent to characteristic zero in some sense. Although recently, Yamaguchi put out a pretty neat result that there's a variant on this, whose test ideal is the multiplier ideal. And that's neat because the multiplier ideal is our big characteristic zero tool. So if you can get a closure whose test ideal is the multiplier ideal, that seems like it would be the right kind of thing to study characteristic zero singularities. But this is computing any of this. Like tight closure is already bad to compute. You need a reduction to characteristic P and to compute tight closure. It's not necessarily easy to do. And the third is parasolid closure. This one is more of a characteristic free kind of idea. it doesn't involve reduction to characteristic P. It involves looking at some elements in local cohomology modules. Again, pretty hard to compute, but is out there, definitely is an attempt at not having to reduce to characteristic P. So what we're working on in our paper is, can we define a closure operation in characteristic 0 that involves no reduction to characteristic P, that's built on the kinds of tools like alterations, like resolution of singularities that people actually use in characteristic 0? And can we find something that you can actually compute? Would be nice. So let me go and define our first one. I'll talk about two. And actually, this is a good pause point for questions. So while I'm erasing, think if you do have some. Plus closure is a module closure.
Okay, what is it? What's
R plus.
like you take the full field program.
No, I don't think that one does. Yeah, I haven't seen that one be used. There's like, with the canonical trace becoming pretty important, you could look at the closure coming from the canonical module for sure. And that module closure is, if the module is finitely generated, you can just compute it in Macaulay too. Like, it's not super complicated.
But in general, these closures, when you say they're hard to compute, do you really, there's no algorithm that you don't compute them?
For tight closure, we only have algorithms for a very, very limited set of rings. For those, okay, ultra products, like, good luck finding an algorithm. The version of reduction to characteristic P where you use a finitely generated Z algebra, I think you could probably turn that into an algorithm. Sort of like, you could describe it, but I don't know if you could turn it into a computer algorithm in a super straightforward way, because you're sort of like, what elements do I need in this containment? I'll adjoin those to Z. Parasolid closure, you would have to check on some elements being 0 or not in certain local cohomology modules. I'm not sure how easy it is to find those elements.
I mean, my understanding is these things are mostly infinite kinds of computations.
Yeah.
But
Yeah, I mean,
it sounds like
well, I mean, right, for these two, you can only compute it if you know how to compute the tight closure for every P, and well, you probably don't. So. Okay. So for probably the rest of the talk, I'm going to assume R is going to contain Q. It's a reduced Noetherian excellent ring. With a dualizing complex. Okay, so this is going to be assumptions for basically everything else. So I probably won't write them in the theorem statements, so worth taking a note. Okay, so here's our first closure. And this is going to be another, I'm defining this in terms of a resolution of singularities, so I can't tell you that much about what the geometry parts mean. So I is going to be generated by like some Fs. The underscore just means like F1, F2, some finite list. Is contained in R. And pi from Y to spec R is a regular alteration. So we're going to define what we're calling the Kazul-Hironaka closure. Which we're going to call KH of I inside R. It's the following. So this homology is Kazul homology with respect to the Fs. So we've got our alteration, resolution stuff. We're looking at a Cazul complex involving the Fs and this thing, which we can treat like it is an algebra, kind of. And this is the part that I understand the least in the whole paper, but apparently you can just kind of say, it's more or less. To get this map, you can go either Cazul first or alteration first. So this is a commutative diagram. You can compute the kernel going either way. So if this notation means something to you, it doesn't matter which way you go. Something that's annoying about this is that Cazul complexes are really something we only have for like a list of elements in the ring. So we really only have this closure defined for ideals. We'd love to find a way to extend it to modules. It's really not obvious how to do that. So that's his weakest point, I think.
Next thing,
Oh, why?
the others.
Oh,
Right.
yeah, right derived, yeah. So
Wait, so is that just cohomology or is that, or?
so it's a
so why
complex.
complex?
Yeah, so this whole thing is a complex. It turns out we can treat it like it's a modular algebra. And that's a great question. I have no idea. This would be a great question for Peter or Carl. So I do think that in a lot of the cases we're working with, it turns out you only have homology in like 1 degree, so it turns out not to be that bad to work with. But also we're working with the H0 in practice. It's missing this. Yes, just H0. Oh, sorry, no, H0. So let me just tell you a bunch of properties of this that don't require any knowledge of algebraic geometry to state the properties, which is great for me. So this is Epstein, McDonald, RG. Okay. So first, this is a well-defined closure operation. And better yet, it's independent both of your choice of the Fs as generators for I and of your choice of regular alteration. You pick one. Yes. Yeah. Yeah, so I think if your ring's not nice enough, it can't possibly be an alteration of itself. So this also has a lot of the properties that make tight closure so exciting. So most of the things I'm going to list next are things tight closure has. One notable exception. So first, this is the one that tight closure doesn't have. So this one actually commutes with localization, which tight closure like pretty famously doesn't have. This one also computes with completion. I'm being a little bit lazy and not writing which ring the I is in here. Let me.
So what is the kind of object is W? So you say it's a two ring set.
Oh, yeah, so what I'm trying to say here is it commutes with localization. So any,
So W is like multiple.
oh, yes, that is what I meant to write, thanks. Yes. So commutes with localization and completion. So in one way, it's better than tight closure. In one way. So it's persistent. So if R to S is a map of rings, so if you take the Kazul-Hironaka closure of I and R and then extend up to S, it's the same as, or it's contained in what you get if you extended the ideal first and then computed the closure. So if you want to work with change of rings kind of things, you can. This is called persistence. And a little bit stronger if it's a finite extension of rings. Then actually we can compute the closure in R by going up to S, computing the closure there, and then just intersect back with R. That's another well-known property of tight closure that it's just sort of nice to have. So,
Should we suggest that it behaves sort of well with flat extension?
yeah, that was the more general result I just didn't put on the board, but yes, that's the result is it plays well with flat extensions. And there's more.
So you were just saying that if you have a flat extension, then you get the same formula.
Yeah,
That's what it's like.
yeah. I should have just put it on the board. Oh, well. So one thing about tight closure is we have like a vague sense of how large it is. In particular, it's smaller than integral closure, and so is this one. So it's not like too large to be useful. And 6 is that this satisfies a whole bunch of colon capturing type properties, which is something that's notable about tight closure and pretty useful. So we'll assume R is local. So then we get so one thing we get is multiplying powers of a parameter into the ideal with the higher power. This colon ideal is contained in the closure. We also get multiplying one parameter into the closure of the ideal generated by the previous ones also contained in the closure of the previous parameters. These are all versions of colon capturing. I feel guilty because in my thesis, I called these like version A and version B, and we haven't found a better name yet. So someday they'll have actually good names. So all of this is just general properties of the closure, but the thing we really wanted to know is how does this relate to singularity types? And so the key thing is that this closure detects rational singularities. So if we have a local ring plus all the hypotheses, I don't know where they've gotten to, but all the hypotheses from earlier. So then the following are equivalent. R has rational singularities. 2, every ideal is KH closed. And 3, some ideal generated by a system of parameters, like a full system of parameters, is KH closed. So this I want to compare to tight closure because it's different for F rational singularities. So for tight closure, is this still up? No, it's long gone. These two things are not the same for tight closure. So every ideal being closed that's something called weakly F regular. And every parameter ideal or some parameter ideal is F rational. So I think this pinpoints really the key difference. This thing is not going to reduce to tight closure and characteristic P. It's a bit smaller. It's really not going to capture things that are less singular than rational singularities, because the moment R has rational singularities, this is the trivial closure on ideals, and we've lost a chance to get more information. But if what you want to know is, does the ring have rational singularities? Like this closure, if you find a system of parameters that's KH closed, you know it does. And that's pretty decent. And so a corollary to all of this is that if R is Cohen-Macaulay, and all of our hypotheses from before, we also need essentially a finite type over a field of characteristic 0. So all of our results so far are just characteristic 0. We don't talk about characteristic P at all. But if you do reduce characteristic P, then the KH test ideal reduces to the parameter test ideal. Which is the intersection of everything that multiplies I star into I, where I is a parameter ideal. And the main other result we get about this closure is we get part of Brianson-Skoda. We'd love to get all of it. It turns out we probably, or definitely don't. Suppose R is a domain, and J has n generators. So then Jn's integral closure is contained in J's Kazul-Hironaka closure. And this is a statement of Brianson-Skoda, but usually there's a version of this where you can replace J with powers of J. And actually we don't get that at all with this closure. So here's an example. So we have in the paper a Macaulay 2 package that will compute anytime you know a resolution of singularities, we can compute the Kazul-Hironaka closure. So using that package, we verified that if R is this ring, And if we set I to be xy, then if we look at I cubed, integral closure is not contained in the Cazorla-Hironaka closure of I squared. So this specifically contradicts the higher power version of Brians and Skoda. So this is pretty solid. I think this is just a really good version of a closure for characteristic 0 in that it has a lot of the properties that make tight closure usable. It detects rational singularities in a pretty straightforward way. And you can literally compute in Macaulay too. The package is on Carl's website and will also be in the paper. It's a pretty brief package, right? This isn't too bad to do in any case where you do know a resolution of singularities. But maybe we'd really like something that is more like the strongly F regular KLT singularities and detects that. So we do have another closure that can do that. So this is going to go back to regular alterations and that definition of the multiplier ideal from Peter's thesis that I put up a while ago. So if we have a regular alteration pi from y to spec r, we'll set first CL pi to be the module closure. And that comes from pi star of omega y, which we can view as an R module. So then the canonical alterations closure is going to be just the intersection over all of these regular alterations, pi from y to spec r, of these module closures of L and M. So as a closure operation, this is actually pretty easy to work with because module closures are extremely easy to work with, and this is an intersection of module closures. It's not bad at all, just from a structure perspective of proving things about this. And the key result is really, so this is a functorial residual closure operation. And if R is normal, local, and essentially a finite type over a field of characteristic 0, then the test ideal of this closure is actually the multiplier ideal. So basically, whenever Peter's result holds, where the multiplier ideal is like a trace ideal, then the test ideal for this closure will agree with the multiplier ideal. And a side note is that for ideals, the Cazorla-Hironaka closure is smaller than the canonical alterations closure. So that's something we wanted to get a bigger closure. Cazorla-Hironaka was so small it could detect rational singularities, but not like KLT. But this one, because its test ideal of the multiplier ideal, does detect KLT singularities. So unsurprising that it's larger.
Multiplier ideal is like the intersection trace ideal overall.
It's going to be a sum of trace ideals, but yes. Yeah. And this is a perspective that Neil Epstein, Janet Vasiliev, and I have been working on for quite a while of just like thinking of things like this. So just to summarize, 'cause I'm out of time. So something else that's true is that for parameter ideals, actually these closures agree. But not on other ideals. So here, if some ideal is generated by a system of parameters, is KH closed, then every ideal is, but that won't be true for cult. because they don't usually agree. And we do get that cult is actually plausibly bigger than tight closure, whereas KH is going to be smaller than tight closure. And there is a Brianson-Skoda result for cult as well. So depending on what you want to do, you might want one of these closures or the other. I would say that from a closure operations perspective, cult is pretty easy to work with. Kazul-Hironaka closure less so. But I think Kazul-Hironaka, the fact that you can just compute it in Macaulay 2 is just fantastic. So I'll stop there.